Right now, as you read these words, as you breathe in and out, as your heart beats its steady rhythm, you are moving through space at an almost incomprehensible speed. Not just spinning with Earth on its axis, not just orbiting the sun, not just traveling with the solar system around the center of our galaxy. You are being pulled, drawn by an invisible hand towards something immense, something hidden, something that lies beyond the edge of what we can easily see. Our entire galaxy, the Milky Way, with its hundreds of billions of stars, its vast spiraling arms of light and darkness, its ancient core and its scattered halo, is falling. We are falling through the universe at more than 600 kilometers every single second. That is over 2 million kilometers every hour. In the time it takes you to sleep through one night, our galaxy will have traveled more than 50 million kilometers toward this mysterious destination. This is not the expansion of the universe carrying us along. This is not the gentle drift of cosmic inflation. This is gravitational attraction, pure and powerful, pulling our galaxy and millions of others toward a concentration of mass so enormous that it defies easy understanding. And yet, for decades, we could not see it. It hides behind a veil of dust and stars, obscured by the very galaxy we call home. This invisible monster of gravity has a name. Astronomers call it the Great Attractor, and its story is one of the most beautiful mysteries in modern cosmology. Let your mind relax as we begin this journey together. There is no need to grasp every detail, no need to memorize every number. Simply let the ideas wash over you like gentle waves. We are going to drift through space and time, following the trail of discovery that led astronomers to realize that our galaxy is not sitting still, not simply expanding with the universe, but actively being pulled towards something vast and hidden. Close your eyes for a moment if you wish, and picture yourself floating high above Earth. You see the blue and white marble turning slowly below you. Now pull back further. Watch as the sun appears, a brilliant point of light, and Earth becomes a tiny speck beside it. Pull back more, and the other planets appear, distant worlds tracing their ancient paths around our star. Keep pulling back. The sun itself becomes just one star among many. The night sky opens up around you in all directions, filled with countless points of light. You are seeing our local neighborhood now, the nearest stars, each one a sun in its own right, many with their own families of worlds. Continue this journey outward. The stars begin to cluster, forming patterns, structures. You start to see the shape of the Milky Way itself, a great spiral of light turning slowly in the darkness. 200 billion stars or more, bound together by gravity, rotating around a common center over the course of hundreds of millions of years. But even this grand rotation is not the only motion. The entire galaxy, as a unified object, is moving through space, drifting, falling, being pulled. For most of human history, we did not know this. We thought the universe was static, unchanging, eternal. Even after we understood that planets orbit the sun, that stars are distant suns, that our galaxy is one of countless others, we still imagined that on the largest scales, everything was more or less at rest. The 20th century shattered that illusion completely. In the 1920s, Edwin Hubble discovered that the universe is expanding. Distant galaxies are moving away from us, and the further away they are, the faster they recede. This was a profound revelation. The universe had a history. It was not eternal and unchanging. It was dynamic, evolving, and at some point in the distant past, everything had been much closer together. This expansion continues today. Space itself stretches, carrying galaxies along with it. On the largest scales, this expansion dominates. Galaxies separated by billions of light years are being carried apart by the stretching of space faster than any rocket or beam of light could ever bring them back together. But Hubble's law, as it came to be called, describes an average behavior. It tells us what galaxies would do if expansion were the only thing happening. The reality is more complex, more interesting, more beautiful. Galaxies also feel the gravitational pull of nearby masses. Our Milky Way and the Andromeda Galaxy, for instance, are being drawn toward each other by their mutual gravity. Despite the expansion of the universe, these two galaxies are approaching, destined to merge billions of years from now. This motion is called a peculiar velocity, the component of a galaxy's motion that deviates from the smooth cosmic expansion. In the 1970s, astronomers began to measure these peculiar velocities with greater precision. They studied how galaxies moved relative to the cosmic microwave background, the faint afterglow of the Big Bang that fills all of space. This radiation provides a natural reference frame, a way to measure absolute motion through the universe. What they found was unexpected. Our galaxy, along with all the galaxies in our local group, and indeed all the galaxies in a vast region of space stretching hundreds of millions of light years, are moving together in the same general direction. Not randomly, not in scattered paths, but flowing like water in a river, converging toward a single region of the sky. The speeds involved are enormous. 600 kilometers per second, more than 2,000 times the speed of sound in Earth's atmosphere, more than 1,000,000 miles per hour. At this velocity, you could travel from Earth to the Moon in 10 minutes. For a galaxy to be moving this fast, something must be pulling it. Something massive. Something containing the gravitational equivalent of tens of thousands of galaxies. The astronomer who first brought widespread attention to this phenomenon was Vera Rubin, though many others contributed to the discovery. Rubin was already famous for her work on galaxy rotation curves, observations that provided some of the strongest evidence for the existence of dark matter. In the late 1970s and early 1980s, she and her colleagues were measuring the velocities of galaxies in various directions across the sky. They noticed a pattern. Galaxies in one hemisphere seemed to be approaching us slightly faster than the expansion of the universe would predict. Galaxies in the opposite hemisphere were receding slightly faster. This created a dipole pattern, a systematic deviation from smooth expansion, pointing in a specific direction. The direction was toward the constellations Hydra and Centaurus in the southern sky as seen from Earth. Something in that direction was pulling not just our galaxy, but all the galaxies in a vast volume of space surrounding us. The name came naturally. If something was attracting all these galaxies, drawing them toward itself with irresistible gravitational force, it deserved a name that captured its nature: the Great Attractor. But here was the problem. When astronomers pointed their telescopes toward that region of the sky, they saw galaxies, yes, but nothing that seemed remotely large enough to account for the motion they were observing. No obvious supercluster, no overwhelming concentration of light. The answer to this puzzle lay in an unfortunate accident of cosmic geography. The Great Attractor lies in a direction that places it almost directly behind the disk of our own Milky Way. And the Milky Way, for all its beauty, is also a barrier, a wall of stars and dust and gas that blocks our view of the distant universe beyond. Astronomers call this region the zone of avoidance. It is a band across the sky, roughly following the plane of the Milky Way, where our view of the distant universe is severely obscured. Like trying to see through a thick fog or through a sandstorm, the light from distant galaxies is absorbed and scattered by the material in our own galactic disk. Invisible light, the zone of avoidance, lives up to its name. We can avoid looking there because we cannot see much of anything. But light comes in many forms, many wavelengths. Visible light, the light our eyes can see, is just one small part of the electromagnetic spectrum. Longer wavelengths, like infrared light and radio waves, can penetrate dust much more effectively. And so, Beginning in the 1980s and accelerating through the 1990s and into the 21st century, astronomers began to map the zone of avoidance using infrared telescopes and radio surveys. Slowly, painstakingly, a picture began to emerge. Behind the obscuring disk of the Milky Way, hidden from easy view, lies an enormous structure. Not a single cluster of galaxies, but a vast overdense region, a supercluster containing many clusters, each cluster containing hundreds or thousands of galaxies. The mass concentration is staggering. Tens of thousands of times the mass of the Milky Way, all concentrated in a region some 150 to 250 million light-years away. This structure has several names. Sometimes it is called the Norma cluster, after one of its prominent components. Sometimes it is referred to as the Great Attractor itself, though as we will see, the situation is even more complex than early astronomers imagined. Imagine standing in a vast, dark room. You cannot see the walls, the ceiling, the floor, but you feel a breeze, always blowing from one direction. You feel it on your face, in your hair, a constant gentle pressure. You know something must be causing this breeze, some opening, some source. But you cannot see it directly. All you can do is feel its effect and reason backward to its cause. This is what astronomers have done with the Great Attractor. They cannot see it directly, not in its entirety, not with the clarity they would wish. But they can measure its effects. They can trace the motion of thousands of galaxies, mapping their velocities, their trajectories, the paths they follow through space. And from these motions, they can infer the presence of enormous concentrations of mass, hidden or partially hidden, pulling everything nearby toward them. The story of the Great Attractor is a story about motion, about the fact that nothing in the universe is truly at rest. Everything moves. Earth orbits the sun orbits the galactic center. The galaxy falls toward its neighbors. And all of this motion, complex and layered, reveals the distribution of mass throughout the universe, the invisible scaffolding of gravity that shapes the cosmos on the largest scales. It is also a story about limits, about the boundaries of what we can see and what we must infer. The universe does not always present itself clearly. Sometimes the most important structures are hidden, obscured, revealed only through patient observation and clever reasoning. As you lie here, relaxing, letting these ideas settle into your mind, consider what it means that you are part of this motion. Every atom in your body, every molecule, every cell, is traveling through space at 600 kilometers per second, pulled by a gravitational force that spans hundreds of millions of light years. You are part of a cosmic current, a river of galaxies flowing through the universe. There is something deeply calming about this realization. Your individual worries, your daily concerns, they are real and they matter, but they are also part of something incomprehensibly larger. You are a passenger on a journey that began billions of years ago and will continue for billions more. The Great Attractor has been pulling our galaxy since long before Earth formed, long before life began, long before the first human looked up at the night sky and wondered what those points of light might be. And it will continue to pull long after we are gone. But the story is not quite finished. Because as astronomers continued to map the motions of galaxies through the 1990s and 2000s, they realized that the Great Attractor itself is not the final destination. It too is moving. It too is being pulled. Beyond the Great Attractor, even further away, lies something even larger. The Shapley Supercluster, a concentration of galaxies so massive that it dwarfs even the structure that originally captured astronomers' attention. And this raises a question that we will explore further. Are we being pulled by the Great Attractor, or through it, towards something even more distant? The answer, as we will see, involves understanding the cosmic web, the largest scale structure in the universe, a vast network of filaments and clusters and voids that spans billions of light years. Our motion, the motion of the Milky Way and all our neighboring galaxies, is not determined by a single massive object, but by the combined gravitational pull of vast regions of the universe, all tugging on us in different directions, the strongest pull winning out, drawing us along a path through space that was determined billions of years ago by the initial distribution of matter after the Big Bang. But we are getting ahead of ourselves. For now, simply rest in the knowledge that you are moving, falling through space, not toward destruction, but toward a distant congregation of galaxies, a gathering place of mass and light and gravity. The journey will take hundreds of millions of years, far longer than humanity has existed, far longer than Earth will remain habitable. We will never arrive, not really, because the expansion of the universe will ultimately win, carrying the Great Attractor away from us faster than we can fall toward it. But the pull is real, the motion is real, and the story of how we discovered this invisible force, this hidden hand guiding our path through the cosmos, is a testament to human curiosity, to our determination to understand the universe even when it hides its secrets behind veils of dust and distance. Let your breathing slow. Let your body relax. We have only just begun this journey, and there is so much more to explore. The Great Attractor awaits, patient and inevitable, pulling us gently forward through the darkness. The cosmic motion. To understand what makes the Great Attractor so remarkable, we must first understand the different ways that galaxies move through the universe. Motion in the cosmos is layered, complex, like a dance with many rhythms playing at once. Each type of motion tells us something different about the structure and history of the universe. The most fundamental motion is the expansion of space itself. This is not motion through space, but motion of space. Imagine a deflated balloon with dots drawn on its surface. As you inflate the balloon, the dots move apart from each other, not because they are traveling across the rubber, but because the rubber itself is stretching, carrying them along. The universe works in a similar way, though in 3 dimensions rather than on a 2-dimensional surface. Space itself is expanding, and galaxies, like dots on that cosmic balloon, are being carried apart by this expansion. The further apart 2 galaxies are, the more space lies between them, and the faster that space expands, carrying them apart at ever-increasing speeds. This expansion was discovered by Edwin Hubble in 1929, though the groundwork had been laid by earlier astronomers and theorists. Hubble measured the distances to nearby galaxies using variable stars as cosmic lighthouses, objects whose brightness changes in predictable ways that allow us to calculate how far away they are. He also measured how fast these galaxies were moving toward or away from us, using the Doppler effect, the same phenomenon that makes a siren sound higher as it approaches and lower as it recedes. What Hubble found was a clear pattern. The further away a galaxy was, the faster it was receding from us. This relationship, now called Hubble's law, revealed that the universe was expanding uniformly in all directions. We are not at the center of this expansion. Every observer, in every galaxy, would see the same pattern. From their perspective, all other galaxies would appear to be moving away, with more distant galaxies receding faster. This expansion is often described using the Hubble constant, a number that relates distance to recession velocity. Today, we measure this constant to be approximately 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light years, a convenient unit for measuring distances between galaxies. What this means is that a galaxy 1 megaparsec away is receding from us at 70 kilometers per second due to cosmic expansion. A galaxy 2 megaparsecs away is receding at 140 kilometers per second. A galaxy 10 megaparsecs away is receding at 700 kilometers per second, and so on. The relationship is linear, simple, elegant, but this describes only the average behavior. It tells us what galaxies would do if expansion were the only thing happening. If the universe were perfectly smooth and uniform, with no concentrations of mass, no gravitational attraction between nearby structures. The real universe is not smooth. It is lumpy, clustered, filled with structure on every scale. And wherever there is mass, there is gravity, pulling nearby objects toward it. This gravitational attraction creates what astronomers call peculiar velocities, the motion of galaxies that deviates from the smooth cosmic expansion. The word peculiar here does not mean strange or unusual. It is an older astronomical term meaning specific or particular, referring to the unique motion of each galaxy on top of the general expansion. Imagine you are on a moving walkway at an airport, the kind that carries you along at a steady pace. The walkway represents cosmic expansion, carrying you and everyone else in a particular direction. But you are not passive. You can walk forward on the walkway, moving faster than it carries you. You can walk backward, moving slower, or even going in the opposite direction. You can step side to side. These additional motions, on top of the motion of the walkway itself, are like peculiar velocities. Our Milky Way has a peculiar velocity. So does every other galaxy. These peculiar velocities are caused by the gravitational pull of nearby mass concentrations. A galaxy near a large cluster will be pulled toward that cluster, giving it a peculiar velocity in that direction. A galaxy between two clusters might be pulled in opposite directions, with the stronger pull dominating. Measuring peculiar velocities is not straightforward. We can easily measure a galaxy's total velocity relative to us using the Doppler shift of its light. But how do we separate the expansion component from the peculiar velocity component? We need a reference frame, a cosmic standard of rest against which to measure motion. Fortunately, the universe provides one. The cosmic microwave background, or CMB, is the faint glow of radiation left over from the Big Bang. It fills all of space uniformly, coming from every direction with nearly the same temperature, about 2.7 Kelvin, just a few degrees above absolute zero. Nearly the same temperature, but not exactly. When we measure the CMB carefully, we detect tiny temperature variations, fluctuations of 1 part in 100,000. Most of these fluctuations are imprinted from the early universe, quantum ripples in the primordial plasma that have been stretched to cosmic scales by expansion. These fluctuations are incredibly important. They are the seeds from which all structure in the universe grew, but they are not what concerns us here. There is another temperature variation in the CMB, much larger and much simpler in pattern. The CMB appears slightly hotter in one direction across the sky and slightly cooler in the opposite direction. This is a dipole pattern caused by our motion through space. Because of the Doppler effect, radiation from a source we are moving toward appears blue shifted to higher frequencies and energies, which for thermal radiation means higher temperature. Radiation from a source we are moving away from appears redshifted, lower in frequency and energy, cooler. Since the CMB surrounds us uniformly, our motion through it creates this dipole, a warm spot ahead and a cool spot behind. By measuring this dipole, astronomers have determined that our solar system is moving at about 370 kilometers per second relative to the CMB. This motion is the sum of several components. Earth orbits the Sun at 30 kilometers per second. The Sun orbits the center of the Milky Way at about 220 kilometers per second. And the Milky Way itself is moving through space, pulled by the gravity of nearby and distant structures. When we account for all these layered motions, we find that the Milky Way, taken as a whole, is moving at roughly 600 kilometers per second in the direction of the constellation Hydra. This motion is not toward the center of our galaxy, not along our orbital path around the galactic core, but in a completely different direction, cutting across the plane of the galaxy, pulling us through space on a path determined by the large-scale distribution of mass in the universe. 600 kilometers per second. Let that number settle in your mind. It is hard to grasp such a speed. There is no human experience that compares. The fastest jet aircraft fly at less than 1 kilometer per second. The space shuttle, in low Earth orbit, traveled at about 8 kilometers per second. Even the Voyager spacecraft, humanity's fastest and most distant emissaries, are traveling at only about 17 kilometers per second relative to the Sun, and they took decades to reach the outer solar system. Our galaxy is moving more than 35 times faster than Voyager, and it carries everything with it. The Sun, Earth, every planet, every asteroid, every comet, every living thing. You, right now, are racing through space at this incredible velocity, utterly unaware because everything around you shares the same motion. This is the nature of inertial motion. When an entire system moves together, when there is no acceleration, no change in velocity, motion becomes undetectable from within the system. You do not feel the motion of Earth around the Sun because you move with Earth. You do not feel the motion of the Sun around the galaxy because you move with the Sun. And you do not feel the motion of the galaxy toward the Great Attractor because you move with the galaxy. But the motion is real, and it carries consequences. Over millions of years, it will change our view of the universe. The positions of distant galaxies in our sky will shift, not just from the expansion of space, but from our motion through it. The Great Attractor region, currently hidden behind the galactic plane, may slowly shift in the sky as we move, though we will never move enough in a human lifetime to notice. This motion also tells us something profound about the universe. It tells us that gravity matters on the largest scales. Even though the universe is expanding, even though distant galaxies are being carried away from us by the stretching of space, gravity is still powerful enough to gather nearby galaxies into clusters, to pull those clusters into superclusters, and to create bulk flows of thousands of galaxies moving together through space. The term bulk flow describes exactly this phenomenon. It is not just our galaxy that is moving toward the Great Attractor. All the galaxies in a vast volume of space around us, extending hundreds of millions of light years, are participating in the same motion, flowing together like water in a cosmic river. This river has many tributaries. The Milky Way is part of a small group of galaxies called the Local Group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller dwarf galaxies. The Local Group is about 10 million light-years across, and all its members are gravitationally bound, orbiting their common center of mass. The Local Group, in turn, is on the outskirts of a larger structure called the Virgo Supercluster, sometimes now called the Local Supercluster. The Virgo Cluster, a concentration of over 1,000 galaxies about 55 million light-years away, forms the heart of this structure. Our Local Group is falling toward the Virgo Cluster, pulled by its gravity, at about 300 kilometers per second. But the Virgo Cluster itself is not stationary. It too is moving, falling toward the Great Attractor at several hundred kilometers per second. And the Great Attractor, as we will see, is part of an even larger structure, a vast filament of galaxies stretching across hundreds of millions of light years. All of these motions add up, vector upon vector, creating the overall flow of galaxies through space. Our peculiar velocity of 600 kilometers per second is the result of all these gravitational influences acting together, pulling us this way and that, with the strongest pull winning out and determining our overall direction. Understanding these motions requires careful observation and complex analysis. Astronomers must measure the distances to thousands of galaxies. Not an easy task when galaxies can be hundreds of millions of light years away. They must measure velocities, determining not just how fast a galaxy is moving, but in what direction, separating the expansion component from the peculiar velocity. One powerful method uses the Tully-Fisher relation, a correlation between the rotation speed of a spiral galaxy and its intrinsic brightness. By measuring how fast a galaxy rotates, we can estimate how bright it actually is. By comparing that to how bright it appears from Earth, we can calculate its distance. Combining distance with observed velocity gives us the galaxy's motion through space. Another method uses surface brightness fluctuations, subtle variations in the light from elliptical galaxies caused by individual stars being slightly brighter or fainter than average. The apparent size of these fluctuations depends on distance. The further away the galaxy, the smaller and more numerous the fluctuations appear. Using these and other techniques, astronomers have measured the distances and velocities of tens of thousands of galaxies, building up a three-dimensional map of the local universe, showing not just where galaxies are, but how they are moving, revealing the currents and flows that shape the cosmic landscape. This work has revealed that the Great Attractor is not an isolated phenomenon. Bulk flows exist throughout the universe, wherever there are large concentrations of mass pulling on surrounding structures. The universe is not expanding smoothly and uniformly. It is expanding in a lumpy, irregular way, with galaxies clustering together, falling toward the largest concentrations, while vast voids, regions of below-average density, expand even faster than the cosmic average. The image that emerges is one of incredible dynamism. The universe is not a static collection of galaxies scattered through space. It is a living, evolving structure, with galaxies moving along invisible highways carved by gravity, flowing toward the densest regions, creating an ever more clustered and filamentary pattern as time goes on. But this motion toward higher density is not unlimited. The expansion of the universe provides a counterforce. On the largest scales, expansion dominates, carrying distant structures apart faster than gravity can pull them together. Only on relatively small scales, up to a few 100 million light years, can gravity create these bulk flows and bound structures. This is why we will never actually reach the Great Attractor, not in any meaningful sense. Even as we fall toward it at 600 kilometers per second, the expansion of space is carrying it away from us. The Great Attractor region is currently about 200 million light years away, give or take. At our current speed, we might expect to reach it in about 300 million years. But the universe is accelerating its expansion, driven by dark energy, a mysterious component that makes up about 70% of the universe's total energy content. Dark energy acts like a repulsive force on the largest scales, causing the expansion to speed up over time. Because of this acceleration, the Great Attractor is receding from us, not as fast as we are approaching, not yet, but fast enough that we will never close the distance. Over the next billions of years, the expansion will continue to accelerate, and eventually, it will carry the Great Attractor region beyond our cosmic event horizon, the boundary beyond which light can no longer reach us. At that point, the Great Attractor will have disappeared from our observable universe, not because it has been destroyed, but because space has stretched so much that its light can no longer complete the journey to us. This is the ultimate fate of all distant structures. The accelerating expansion of the universe will eventually isolate every cluster of galaxies, turning each one into an island universe, surrounded by an ever-growing gulf of empty space. Billions of years from now, a civilization arising in a galaxy far from ours might look out at the sky and see no other galaxies at all, no evidence of a larger universe, no hints of the cosmic web that once connected everything. But that is far in the future, so far that it is almost beyond imagining. For now, We live in a golden age of cosmology, a time when the universe is old enough to have developed rich structure, but young enough that we can still observe that structure, map it, understand it. The motion of our galaxy toward the Great Attractor is part of that structure. It is evidence of the gravitational scaffolding that shapes the cosmos, the invisible framework of dark matter and ordinary matter that guides the paths of galaxies through space. Every measurement of peculiar velocity, every map of bulk flows, every discovery of a new supercluster or void adds to our understanding of this scaffolding, revealing the universe's architecture in ever greater detail. As you rest here, breathing slowly, letting these ideas drift through your mind, imagine yourself riding along with the Milky Way on its long journey through space. You are a passenger on a galaxy-sized ship, traveling at 600 kilometers per second through the cosmic ocean. You cannot feel the motion, cannot see it directly, but it is real. It has been happening for billions of years, carrying our galaxy along a path determined by the distribution of matter throughout the universe. There is a peacefulness to this image. You are not in control of this motion. You cannot change it, cannot stop it, cannot alter its course. You simply go along, part of something vast and ancient, following a trajectory laid down long before you were born. And yet, this motion connects you to the universe in a profound way. The same gravity that pulls our galaxy through space is the gravity that holds you to Earth, that keeps the moon in orbit, that binds together the stars in their cosmic dance. It is all one force, one fundamental interaction, shaping everything from the smallest scale to the largest. Let that connection settle into your awareness. Let it bring a sense of calm, a feeling of being part of something larger than yourself, larger than humanity, larger even than our planet or our galaxy. You are part of the cosmos, and the cosmos is in motion, flowing through space according to laws we are only beginning to fully understand. The Great Attractor awaits, invisible but inevitable, pulling us gently forward through the darkness. There is a region of the sky that astronomers have learned to avoid, not out of superstition or fear, but out of practical necessity. This region forms a band across the heavens, roughly following the plane of our Milky Way galaxy, where the view outward into the distant universe becomes murky, obscured, difficult to penetrate. It is called the zone of avoidance, and it is both a blessing and a frustration. The blessing is that it exists at all, because the zone of avoidance is simply the consequence of living inside a magnificent spiral galaxy, surrounded by billions of stars, clouds of gas and dust, the very material that makes galaxies beautiful and alive. The frustration is that this same material blocks our view, creating a blind spot in our cosmic vision, hiding some of the most important structures in the nearby universe. And as fate would have it, the Great Attractor lies almost directly behind this veil. To understand why this matters, imagine yourself standing in a dense forest at night. You know there is a mountain somewhere beyond the trees, because you feel a wind coming from that direction, because you heard stories from travelers who approached from different angles, because the stars seem to align in a way that suggests something massive blocking part of the sky. But you cannot see the mountain directly. The trees are too thick, the darkness too complete. You can only infer its presence, deduce its location, estimate its size from indirect evidence. This is the situation astronomers faced when they realized that our galaxy's motion pointed toward a region of space that lay behind the obscuring disk of the Milky Way. They could measure the motion. They could calculate where the Great Attractor must be. But they could not see it, not clearly, not with the tools available in the early days of its discovery. The Milky Way is a disk-shaped galaxy, a flat spiral approximately 100,000 light-years in diameter, but only a few thousand light-years thick in most places. Our solar system lies within this disk, about 2/3 of the way out from the center, embedded in one of the spiral arms. This gives us a spectacular view of the galaxy from the inside. On a dark night, far from city lights, you can see the Milky Way stretching across the sky like a river of faint light, a glowing band composed of billions of stars too distant to see individually, blending together into a luminous haze. But this same disk that creates such beauty also creates a problem. Between us and the distant universe beyond, in certain directions, lie countless stars, vast clouds of gas, and enormous quantities of dust. This dust, composed of tiny particles of carbon, silicon, and other elements forged in the hearts of stars and scattered into space, is particularly troublesome. It absorbs and scatters light, especially visible light, the wavelengths our eyes are designed to see. When we look toward the plane of the Milky Way, in directions where our line of sight passes through the thickest parts of the galactic disk, the dust can reduce the brightness of distant objects by factors of thousands or even millions. A galaxy that would appear bright and clear in an unobscured direction might become completely invisible when viewed through the dust of the galactic plane. It is like trying to see through smoke or fog. The light is scattered and absorbed before it can reach us. The zone of avoidance is not a fixed, well-defined region. It is more like a gradient, a region where obscuration gradually increases as we look closer to the galactic plane. Near the poles of the galaxy, perpendicular to the disk, our view is clear. We can see billions of light years into space, observing distant galaxies with relatively little interference. But as we look closer to the galactic equator, the extinction increases and more of the distant universe disappears from view. At its worst, in the densest regions of the galactic plane, the zone of avoidance can obscure up to 20% of the entire sky. This is not a small problem. Imagine trying to understand the geography of Earth if 20% of the planet were hidden under permanent cloud cover. You could map the clear regions, study them in detail, but there would always be gaps in your knowledge, missing pieces that might contain important features, crucial connections. For decades after the discovery of the Great Attractor, this is exactly the situation astronomers faced. They knew something massive lay in the direction of hydra-centaurus. They could measure its gravitational effect on surrounding galaxies. They could estimate its distance, roughly 150 to 250 million light years away. But they could not see it directly because it lay behind the thickest part of the zone of avoidance. The solution came from a fundamental property of light itself. Light is an electromagnetic wave, and it comes in many different wavelengths. Visible light, the light our eyes detect, spans wavelengths from about 400 nanometers, which we perceive as violet, to about 700 nanometers, which we perceive as red. But the electromagnetic spectrum extends far beyond these narrow bounds. Longer wavelengths include infrared light, microwaves, and radio waves. Shorter wavelengths include ultraviolet light, X-rays, and gamma rays. Each part of the spectrum interacts with matter in different ways. Some wavelengths are absorbed easily. Others pass through material that would be opaque at other wavelengths. Dust, it turns out, scatters and absorbs short wavelengths much more efficiently than long wavelengths. This is why the sky appears blue. Shorter wavelengths of sunlight scatter more in Earth's atmosphere, filling the sky with blue light. It is also why sunsets appear red when the sun is low on the horizon. Its light passes through more atmosphere, and the blue wavelengths are scattered away, leaving the red. The same principle applies to interstellar dust. Visible light, particularly blue light, is strongly affected. But infrared light, with wavelengths longer than what our eyes can see, passes through dust much more easily. Infrared observations can penetrate regions that appear completely opaque at visible wavelengths, revealing structures hidden behind the veil. Beginning in the 1980s, and accelerating through the 1990s and into the 21st century, astronomers began systematic surveys of the zone of avoidance using infrared detectors. These surveys had names like IRAS, the Infrared Astronomical Satellite, and later 2MASS, the 2-micron all-sky survey. They scanned the sky at infrared wavelengths, building up maps of the hidden universe behind the galactic plane. What they found was remarkable. Behind the dust, in the direction of the Great Attractor, lay not one cluster of galaxies, but several, a complex structure of multiple concentrations spread across tens of millions of light years. One of the most prominent is called the Norma cluster, named after the constellation Norma, the Carpenter's square, in whose direction it lies. The Norma cluster is a rich concentration of galaxies, containing hundreds of bright members and likely thousands of smaller, fainter galaxies. Its total mass is estimated at several thousand times the mass of the Milky Way, enough to create a significant gravitational pull on surrounding structures. But it is not alone. Nearby, also hidden behind the galactic plane, are other clusters and groups, all part of a larger structure sometimes called the Great Attractor Supercluster, or more recently, identified as part of the Norma hydra-centaurus supercluster. This supercluster is vast. It extends across more than 100 million light years, containing multiple rich clusters, each cluster a city of galaxies, bound together by gravity. The total mass of this structure is estimated at around 10 to the power of 16 solar masses, 10,000 trillion times the mass of our Sun, or about the mass of 50,000 Milky Way galaxies. This is more than enough to account for the peculiar velocities observed in the local universe. The gravitational pull of such a concentration would indeed draw surrounding galaxies toward it, creating the bulk flow that astronomers had measured. The Great Attractor, it seemed, had been found. But even this discovery did not complete the picture. As observations continued, as astronomers measured velocities of more and more distant galaxies, it became clear that the story was even more complex. The Great Attractor itself appeared to be moving, participating in an even larger bulk flow that extended hundreds of millions of light years, far beyond the Norma hydra-centaurus supercluster. Beyond the Great Attractor, in the same general direction but about 4 times more distant, lies the Shapley Supercluster, the largest concentration of galaxies in the nearby universe. The Shapley Supercluster contains more than 25 times the mass of the Great Attractor region, making it a truly colossal structure, one of the most massive superstructures known. Is our motion directed toward the Great Attractor, or is the Great Attractor itself just a waypoint, with both it and us being pulled toward the even more distant Shapley Supercluster? This question has no simple answer, because gravity does not work in straight lines when you have multiple massive objects pulling in different directions. The actual motion of any galaxy is determined by the combined gravitational influence of all nearby and distant structures, weighted by their mass and distance. Think of it like this. Imagine you are adrift in a calm sea, but there are currents, some strong, some weak, pulling you in various directions. The current you feel at any moment is the sum of all these influences. You might be pulled most strongly toward the nearest whirlpool, but there is also a broader current carrying you and the whirlpool both toward a more distant drain. Your path is not simply toward one or the other, but a complex curve determined by all the forces acting on you. This is the situation with the Great Attractor. It pulls on us. The Shapley Supercluster pulls on us. The Virgo cluster pulls on us. Countless other structures, some visible, some still hidden, all contribute to our motion. The Great Attractor got its name because it was the first major concentration identified in the direction of our bulk motion, but it is part of a larger pattern, a region of higher than average density extending across hundreds of millions of light years. Radio observations have also played a crucial role in mapping the zone of avoidance. Radio waves have even longer wavelengths than infrared light, and they penetrate dust and gas almost without hindrance. Radio telescopes can detect the emission from hydrogen gas in distant galaxies using the famous 21-centimeter line, a specific wavelength at which hydrogen naturally radiates. By mapping this emission, astronomers can locate galaxies even when they are completely invisible at optical wavelengths. These multi-wavelength surveys, combining infrared, radio, and when possible, visible light observations, have gradually filled in the map of the zone of avoidance. It is still the most poorly understood region of the nearby universe, and it likely always will be, because we can never move outside our galaxy to get a clearer view. But we now have a much better picture of what lies behind the veil than we did 40 or 50 years ago. The Great Attractor region, once a complete mystery, is now understood to be a complex of galaxy clusters and superclusters, a major node in the cosmic web, a gathering place where galaxies congregate in large numbers, drawn together by gravity over billions of years. It is not a single object, not a giant galaxy or a supermassive black hole, but a region of overdensity, a place where the universe has more matter than average, and where that matter exerts a collective gravitational influence on everything nearby. As you rest here, let your mind wander through this obscured region of space. Picture the dust clouds of the Milky Way stretching across your view, blocking the light from distant galaxies. Then imagine switching your vision, seeing in infrared or radio waves, watching as the veil becomes transparent and thousands of galaxies appear, clustering together, forming groups and chains, all moving slowly through space, falling toward their common center of mass. This is the hidden architecture of the cosmos, the structure that exists whether we can see it or not. The zone of avoidance reminds us that our perspective is limited, that we see the universe from one particular vantage point, and that there are always gaps in our knowledge, regions we cannot observe directly, mysteries that require patience, creativity, and multiple approaches to unravel. The Great Attractor is no longer invisible. We have pierced the veil, mapped its structure, measured its mass. But it remains hidden in a different sense, camouflaged by distance and obscuration, revealed only to those who know how to look, who understand that light comes in many forms, and that the universe can be observed in wavelengths our eyes were never designed to see. This is the nature of astronomical discovery. We are trapped on a small planet, orbiting an ordinary star, in the outer regions of a typical spiral galaxy. We cannot travel to distant galaxies to observe them up close. We cannot move outside the Milky Way to get a clearer view of the structures beyond. We can only work with the light that reaches us, using every tool at our disposal, every wavelength we can detect, building up a picture piece by piece, inference by inference, until the hidden universe reveals itself. And it does reveal itself, slowly, patiently, to those who look carefully and think deeply. The zone of avoidance is no longer avoided. It is explored, mapped, understood. And the Great Attractor, once the greatest mystery in the local universe, is now a known quantity, a measured structure, taking its place in our growing understanding of the cosmic web that connects all galaxies across billions of light years of space. Let your breathing slow, your body relax. The hidden has been revealed, and we continue our journey deeper into the structure of the universe, toward an understanding of what the Great Attractor truly is, and what it means for our galaxy's long journey through the cosmos. Now that we have pierced the veil of the zone of avoidance, now that we can see through the dust and gas of our own galaxy to glimpse what lies beyond, we can begin to answer the question that has guided us from the beginning. What is the Great Attractor? What is this invisible hand pulling our galaxy and millions of others through space at hundreds of kilometers per second? The answer, like so many answers in cosmology, is both simpler and more complex than we might have expected. The Great Attractor is not a single object. It is not a supergalaxy, millions of times larger than the Milky Way. It is not a massive black hole lurking in the depths of space. It is something more subtle, more distributed, and in its own way, more beautiful. The Great Attractor is a region of overdensity, a place where the universe has more matter than average, where galaxies congregate in unusually large numbers, where the gravitational field is stronger than in the surrounding space. It is a node in the cosmic web, a concentration point in the vast network of structures that spans the observable universe. To understand what this means, we must first understand how structure forms in the universe, how the smooth, nearly uniform distribution of matter that existed shortly after the Big Bang evolved into the complex, clustered, filamentary pattern we observe today. In the beginning, immediately after the Big Bang, the universe was extraordinarily smooth. Matter and energy were distributed almost perfectly uniformly throughout space. Almost, but not quite. There were tiny variations, quantum fluctuations stretched to cosmic scales by the rapid expansion called inflation. These fluctuations were incredibly small, density differences of only 1 part in 100,000, but they were enough. Where the density was slightly higher than average, gravity pulled in more matter, making it denser still. Where the density was slightly lower than average, matter flowed outward toward the denser regions, making the underdense areas even emptier. This process, called gravitational instability, amplified the initial tiny fluctuations over billions of years, growing them from microscopic ripples into galaxies, clusters of galaxies, and superclusters. But this growth did not happen uniformly in all directions. The fluctuations had structure, patterns on different scales. Some regions became overdense in elongated shapes, forming filaments. Others became overdense in sheet-like configurations, forming walls. At the intersections of filaments, where multiple streams of matter converged, the density grew especially high, forming massive clusters and superclusters. The result is what cosmologists call the cosmic web, a vast interconnected network of filaments, walls, clusters, and voids that extends throughout the observable universe. On the largest scales, this web is remarkably uniform. Every region of space, when averaged over a few hundred million light years, has roughly the same density. But on smaller scales, the distribution is highly structured, with matter concentrated along the filaments and nodes of the web, and vast empty regions, the cosmic voids, in between. The Great Attractor is one of these nodes. It is a place where multiple filaments converge, where streams of galaxies flow together, creating a concentration of mass large enough to gravitationally influence structures hundreds of millions of light years away. The region contains several major galaxy clusters, each cluster a bound system of hundreds or thousands of galaxies, all orbiting their common center of mass. These clusters, along with smaller groups and individual galaxies between them, form a structure that astronomers now identify as part of the Norma hydra-centaurus supercluster. A supercluster is a vast assembly of galaxy clusters and groups, spanning tens to hundreds of millions of light years, containing the mass of tens of thousands of Milky Way galaxies. Superclusters are among the largest structures in the universe, bound together not as tightly as individual galaxy clusters, but still connected by gravity, still influencing each other's motion, still forming recognizable structures in the cosmic web. The Norma cluster, which lies at the heart of the Great Attractor region, is one of the densest parts of this supercluster. It contains hundreds of bright galaxies and thousands of fainter ones, all moving through space together, bound by their mutual gravitational attraction. The cluster's center lies about 220 million light-years from us, though different measurements give slightly different values, and the structure extends across tens of millions of light-years, making it difficult to define a precise boundary. The total mass of the Great Attractor region is estimated at roughly 10 to the power of 16 solar masses. To give you a sense of scale, our Milky Way galaxy contains about 10 to the power of 12 solar masses, counting all the stars, gas, dust, and dark matter. The Great Attractor contains 10,000 times that mass, concentrated in a region about 300 million light-years in diameter. This is enough mass to create a gravitational well deep enough to pull surrounding galaxies toward it at hundreds of kilometers per second. But mass is not the whole story. Most of the mass in the Great Attractor, like most of the mass everywhere in the universe, is not ordinary matter, not stars and gas and dust, but dark matter, the mysterious substance that makes up about 85% of all matter in the cosmos. Dark matter does not emit light. It does not absorb light. It does not interact with electromagnetic radiation at all, as far as we can tell. The only way we know it exists is through its gravitational effects. Dark matter pulls on ordinary matter, shaping the motion of stars within galaxies, holding galaxy clusters together, and creating the large-scale structure of the universe. In the Great Attractor region, as everywhere else, dark matter provides the gravitational scaffolding. Ordinary matter, the galaxies we can see, traces this underlying structure, congregating where the dark matter is densest, forming visible markers of an invisible framework. When astronomers measure the mass of the Great Attractor, they are measuring primarily dark matter, with the visible galaxies making up only a small fraction of the total. Understanding the role of dark matter is crucial to understanding how the Great Attractor influences our motion. The gravitational pull we feel comes mostly from dark matter, not from the stars and gas we can observe. The visible galaxies are just the tip of the iceberg, the luminous portion of a much larger, much more massive structure. One way to probe this invisible mass is through gravitational lensing. According to Einstein's theory of general relativity, mass curves space and time, and light follows the curves. When light from a distant galaxy passes near a massive structure like a galaxy cluster, its path is bent, causing the distant galaxy to appear distorted, magnified, or multiply-imaged. By studying these lensing effects, astronomers can map the distribution of mass in the intervening structure, including the dark matter that dominates its mass budget. For the Great Attractor region, lensing studies confirm what velocity measurements suggest. There is indeed a vast concentration of mass, much of it dark matter, creating the gravitational well that draws surrounding galaxies inward. But the story does not end with the Great Attractor. As astronomers extended their velocity surveys to greater distances, measuring the motion of galaxies hundreds of millions of light-years away, they found that the bulk flow extends far beyond the Great Attractor region. Our galaxy, the Great Attractor, and thousands of other galaxies are all participating in a much larger flow, a river of galaxies streaming across hundreds of millions of light-years of space. This discovery led astronomers to look further in the same general direction, beyond the Great Attractor, to see what might be driving this extended flow. What they found was the Shapley Supercluster, also known as the Shapley concentration, one of the most massive structures in the nearby universe. The Shapley Supercluster lies about 650 million light-years away, roughly 4 times more distant than the Great Attractor. It is enormous, containing more than 25 times the mass of the Great Attractor region, with an estimated total mass exceeding 10 to the power of 17 solar masses. This makes it one of the largest concentrations of galaxies within 1 billion light-years of the Milky Way. The Shapley Supercluster contains dozens of rich galaxy clusters, each comparable to or larger than the Virgo cluster, the nearest large cluster to us. These clusters are packed relatively closely together, forming a dense core surrounded by a halo of smaller groups and individual galaxies. The entire structure extends across more than 100 million light-years, a significant fraction of a billion light-years. With such enormous mass, the Shapley Supercluster creates a correspondingly strong gravitational pull. Its influence extends across vast distances, affecting the motion of galaxies hundreds of millions of light-years away. Computer simulations of large-scale structure formation suggest that much of the bulk flow in our region of the universe may be driven not primarily by the Great Attractor, but by the combined pull of the Great Attractor and the more distant, more massive Shapley Supercluster. This does not diminish the importance of the Great Attractor. It remains a major concentration of mass, a significant node in the cosmic web, and the dominant structure within 300 million light-years in its direction. But it is part of a larger pattern, a series of overdensities stretching across the sky, all contributing to the overall gravitational landscape that shapes our galaxy's motion. Imagine you are sailing on an ocean with multiple currents. There is a strong current pulling you toward a nearby whirlpool, but there is also a broader current carrying both you and the whirlpool toward a more distant drain. Your actual path is determined by the combination of both currents, along with others you may not even be aware of. You are not moving toward just one destination, but following a complex trajectory shaped by multiple influences. In 2014, a team of astronomers led by Brent Tully published a remarkable map of the local universe, showing how galaxies are organized into larger structures based on their motions. They called this structure Laniakea, a Hawaiian word meaning immeasurable heaven. The Laniakea Supercluster includes the Milky Way, the Virgo cluster, the Great Attractor region, and many other galaxy groups and clusters, all within a region about 500 million light-years in diameter. Laniakea is defined not by the positions of galaxies, but by their motions, by the flow of galaxies through space. It is a gravitational basin, a region of space from which galaxies flow inward toward a common center. That center lies in the Great Attractor region, making the Great Attractor the gravitational heart of Laniakea, the point toward which all nearby galaxies are falling. But even Laniakea is not isolated. It is part of the larger cosmic web, connected to other superclusters by filaments of galaxies, separated from them by vast voids. And the Shapley Supercluster, while more distant, may represent a separate, even larger basin of attraction, pulling on Laniakea itself, creating flows on scales larger than any individual supercluster. This nested hierarchy of structures, flows within flows, attractions within attractions, reveals the complexity of the cosmic web. There is no single center, no ultimate attractor pulling everything toward one point. Instead, there are multiple centers at different scales, each dominating its own region, each participating in larger motions, all the way up to the largest scales where cosmic expansion finally dominates and gravitational influence fades. As you lie here, breathing slowly, letting your body relax, picture this vast structure in your mind. Imagine billions of galaxies, each a city of stars, scattered across hundreds of millions of light-years, all moving through space, all following paths carved by gravity, by the distribution of matter throughout the universe. Picture the filaments of the cosmic web, chains of galaxies stretching across the void, connecting clusters and superclusters. Picture the voids, vast empty regions where few galaxies exist, expanding faster than the cosmic average. Picture the nodes, the dense concentrations where filaments meet, where gravity is strongest, where galaxies congregate in their thousands. The Great Attractor is one such node, a gathering place, a concentration point. It is not special in the sense of being unique. There are many similar structures throughout the universe. But it is special to us because it lies in the direction we are moving, because its gravity shapes our galaxy's path through space, because it represents a destination we will never quite reach, a goal that recedes even as we approach it. This is what the Great Attractor is. Not a monster, not a threat, but a natural consequence of the way structure forms in an expanding universe. A place where matter has gathered, where gravity is strong, where the fabric of space-time curves more deeply than in the surrounding regions. A landmark in the cosmic landscape, guiding our motion through the universe, one of countless such landmarks scattered throughout the vast web that connects all galaxies across billions of light years of space and time. Let this understanding settle into your mind. Let it bring a sense of order, a feeling that the universe, vast and complex as it is, follows patterns we can understand, structures we can map, motions we can predict. The Great Attractor is no longer a mystery. It is known, measured, understood, taking its place in the grand tapestry of cosmic structure that astronomers have spent decades patiently unraveling, thread by thread, observation by observation, until the hidden becomes visible and the chaos reveals itself as elegant order. To truly understand the Great Attractor and its place in the universe, we must step back and look at the largest scales of all, the grand architecture that encompasses everything we have discussed so far. We must explore the cosmic web, the vast network of structure that spans the entire observable universe, connecting galaxies across billions of light years in a pattern of astonishing beauty and complexity. The cosmic web is one of the most remarkable discoveries of modern cosmology. It reveals that the universe is not a random scatter of galaxies, but an organized structure, a network as intricate as a spider's web or the neural connections in a brain, with matter concentrated along filaments and nodes, and vast empty regions in between. This structure emerged gradually from the nearly smooth distribution of matter that existed shortly after the Big Bang. Those tiny initial fluctuations, density variations of only 1 part in 1/100.000, grew over billions of years through gravitational instability, forming first small clumps, then larger structures, and finally the grand cosmic web we observe today. Imagine the early universe as a nearly flat landscape with subtle undulations, gentle rises and shallow depressions barely visible to the eye. Now imagine that this landscape is covered with a thin layer of water. The water will naturally flow from the higher regions toward the lower ones, pooling in the depressions, draining away from the rises. Over time, the landscape becomes more varied. The depressions deepen as water collects in them. The high regions become drier and more barren. Streams form, connecting the pools, carved by the flow of water seeking the lowest points. This is roughly how the cosmic web formed, though with matter flowing under gravity rather than water flowing downhill. Regions that began slightly denser attracted more matter, becoming denser still. Regions that began slightly less dense lost matter to the denser regions, becoming emptier. Stria. The result, visible in modern galaxy surveys that map millions of galaxies across billions of light years, is a structure that resembles a three-dimensional sponge or foam. Galaxies are concentrated along thin filaments, typically only a few tens of millions of light years thick, but stretching across hundreds of millions of light years. These filaments connect at dense nodes, the galaxy clusters and superclusters that mark the most massive concentrations. And between the filaments lie vast voids, regions of space with very few galaxies, ranging from 50 to 300 million light years in diameter. This is not merely structure we observe. It is structure that computer simulations, starting from the known initial conditions of the early universe and following the laws of gravity and cosmic expansion, naturally produce. When cosmologists simulate the formation of structure in the universe, feeding in the observed properties of dark matter, dark energy, and ordinary matter, the simulations spontaneously generate a cosmic web remarkably similar to what we observe. This agreement between theory and observation is one of the great successes of modern cosmology, confirming that we understand, at least in broad strokes, how structure forms in an expanding universe. The filaments of the cosmic web are not thin lines but extended structures, regions where galaxies form an elongated distribution, often described as walls or sheets when viewed edge-on. A typical filament might contain dozens or hundreds of galaxies, streaming along its length, falling toward the dense nodes at either end. The flow of galaxies along filaments is one of the most striking features of the cosmic web, a river-like motion on scales of hundreds of millions of light years. The Great Attractor lies at the intersection of several such filaments. Galaxies flow toward it from multiple directions, converging on this node from vast distances. Our Milky Way, along with the local group in the Virgo cluster, is part of one such stream, falling along a filament toward the Great Attractor region. Other streams, originating from different directions, also converge there, creating a complex pattern of motion that astronomers have spent decades mapping. One of the most powerful tools for mapping these flows is measuring the peculiar velocities of thousands of galaxies, determining not just where they are, but how fast they are moving and in what direction. This requires measuring both distances, which tells us where a galaxy is in three-dimensional space, and redshifts, which combined with distances tells us how much of a galaxy's motion is due to cosmic expansion and how much is peculiar velocity caused by gravitational attraction. These measurements are challenging. Distances to galaxies hundreds of millions of light years away are difficult to determine accurately. Methods like the Tully-Fisher relation for spiral galaxies or the fundamental plane relation for elliptical galaxies provide estimates, but with uncertainties that can be 10 or 20%. Despite these challenges, patient observation of thousands of galaxies has gradually built up a three-dimensional map of the local universe, showing both structure and motion. One particularly important survey is called Cosmic Flows, a project that has measured distances and velocities for tens of thousands of galaxies within a billion light years. By mapping how galaxies move, the Cosmic Flows team has traced the filaments and nodes of the cosmic web, revealing the gravitational landscape that shapes galaxy motions. The 2014 map of Laniakea, which we mentioned earlier, was produced using Cosmic Flows data. By calculating the velocity field, the pattern of how galaxies are moving throughout a vast region of space, astronomers identified the boundaries of Laniakea, separating it from neighboring superclusters based on the direction of flow. Galaxies within Laniakea are all flowing toward the Great Attractor region. Galaxies outside Laniakea are flowing toward different attractors, different nodes in the cosmic web. This flow-based definition of structure is more physically meaningful than simply grouping galaxies by position. It identifies regions that are gravitationally connected, where all galaxies share a common fate, falling toward the same center. It reveals the cosmic web not as a static pattern of positions, but as a dynamic network of flows, a living structure evolving under the influence of gravity. The voids between the filaments are not completely empty, but they are remarkably sparse compared to the filaments and nodes. A typical void contains perhaps 1/10 the average density of the universe, meaning galaxies are 10 times less common there than in an average region of space. Some voids are even more empty, with densities a few percent of the cosmic average. Voids expand faster than the cosmic average because they have less matter and therefore less gravity to slow the expansion. Over time, this causes voids to grow while the surrounding filaments and nodes become denser and more concentrated. The cosmic web is not a static structure, but an evolving one, growing more pronounced with time, at least until dark energy's accelerating expansion begins to dominate on the largest scales. Inside a void, a galaxy would experience very different conditions than in a filament or cluster. There would be few nearby neighbors, little gravitational pull from any particular direction, and the local expansion rate would be higher than average. Such a galaxy would be isolated, drifting through vast empty space, rarely encountering other galaxies, evolving in solitude. In contrast, a galaxy in a dense cluster experiences strong gravitational interactions with its neighbors. Galaxies in clusters move at high speeds, hundreds or thousands of kilometers per second relative to the cluster center. They pass close to each other frequently, sometimes colliding and merging, sometimes stripping gas and stars from each other through tidal forces. The hot gas that fills the space between galaxies in a cluster can also strip gas from individual galaxies as they move through it, a process called ram pressure stripping. These environmental effects shape how galaxies evolve. Galaxies in dense clusters tend to be older, redder, with less active star formation because their gas has been stripped away or used up. Galaxies in filaments, and especially in voids, tend to be younger, bluer, with more ongoing star formation because they retain their gas and continue forming new stars. The cosmic web therefore not only organizes galaxies in space, but also influences their properties, their evolution, their very nature. Where you live in the universe matters. A galaxy in a dense cluster has a different history and a different future than an isolated galaxy in a void. The Great Attractor, as a major node in this web, is a place where many galaxies come together, where interactions are common, where the environment is dynamic and dense. It is a cosmic metropolis, a gathering place where galaxies have been congregating for billions of years, drawn together by gravity, building up a massive concentration that in turn attracts more galaxies, creating a self-reinforcing process that makes the rich get richer and the empty get emptier. This process has a limit, however. Cosmic expansion eventually wins on large enough scales. The Shapley Supercluster, though more massive than the Great Attractor, is distant enough that cosmic expansion is carrying it away from us faster than we can fall toward it. We are moving toward the Great Attractor, and the Great Attractor is part of a larger flow toward Shapley, but we will never actually reach Shapley because expansion will carry it beyond our reach. This sets a natural scale for structure in the universe. Structures up to a few 100 million light-years can be gravitationally bound, or at least gravitationally influenced. Beyond that, expansion dominates, and gravitational influence becomes negligible. The cosmic web extends across billions of light-years, but the flows within it are confined to relatively local regions, a few 100 million light-years across, each region falling toward its nearest major attractor. On the very largest scales, beyond 1 billion light-years, the universe becomes remarkably uniform. The cosmic web continues, but when averaged over such large volumes, every region looks statistically similar to every other region. The same density, the same mix of filaments, nodes, and voids repeated across the observable universe. This is called the cosmological principle, the assumption that the universe is homogeneous and isotropic on sufficiently large scales, looking the same everywhere and in every direction. The cosmic web does not violate this principle. It is structure on intermediate scales, large compared to galaxies and clusters, but small compared to the observable universe. Zoom in, and you see intricate detail, filaments, and voids and flows. Zoom out far enough, and the details blur together into smooth uniformity, like a photograph that appears uniform from a distance but reveals texture and structure when examined closely. As you rest here, Let your mind wander through this vast web. Picture yourself floating high above the universe, looking down on billions of galaxies scattered across space. See how they are not random, but patterned, clustered, connected. See the filaments stretching like threads, the nodes glowing brightly where many filaments meet, the voids like dark bubbles between the shining structure. Now imagine zooming in, following one particular filament toward one particular node. That node is the Great Attractor. See the galaxies streaming toward it from all directions, flowing along filaments, converging on this node from vast distances. Our own galaxy, a small speck among billions, riding one of these streams, carried along by the current, part of a vast migration that has been underway for billions of years. There is something deeply satisfying about this image. The universe is not chaos. It is ordered, structured, organized by gravity into beautiful patterns. The Great Attractor is part of that order, a landmark in the cosmic landscape, a destination on our galaxy's long journey through space and time. And yet, this order is temporary. The cosmic web is a structure of the current epoch, the result of billions of years of gravitational growth from tiny initial seeds. But it will not last forever. As dark energy continues to accelerate the expansion of the universe, structures will become increasingly isolated. Filaments will stretch and thin. Flows will weaken and eventually reverse as expansion overcomes gravitational attraction. Billions of years in the future, the cosmic web will begin to dissolve, its threads pulled apart by the relentless expansion of space. But that is far in the future, so far that it feels almost unreal. For now, in this cosmic epoch, the web exists in all its glory, and we are privileged to observe it, to map it, to understand our place within it. The Great Attractor is our local landmark, the brightest node in our region of the web, the gravitational beacon guiding our motion through the universe. Let this understanding settle into your awareness. Let it bring a sense of connection, a feeling of being part of something vast and ancient and beautiful. The cosmic web connects all galaxies, including ours, in a network of gravity and motion that spans the entire observable universe. You are part of that web, riding along with your galaxy, following a path determined billions of years ago by the initial distribution of matter after the Big Bang, flowing through space toward a distant gathering place you will never reach, but which shapes your journey nonetheless. The web is real. The flows are real. The Great Attractor is real. And you, right now, are participating in this grand cosmic motion. A passenger on a galaxy traveling at 600 kilometers per second through a universe structured by gravity into the most magnificent architecture imaginable. Rest in that knowledge. Let it fill you with wonder and calm as we continue our journey toward understanding what this motion means for our future. We have traveled far in our exploration of the Great Attractor. We have discovered its location, hidden behind the zone of avoidance. We have measured its mass, estimated at tens of thousands of Milky Way galaxies worth of matter. We have mapped its place in the cosmic web, a major node where filaments converge and galaxies flow together. Now we must ask the question that naturally follows from all of this. What is our destiny? Where is this motion taking us? Will we ever reach the Great Attractor? The answer is both simple and profound. No, we will never arrive. This may seem strange at first. We are moving toward the Great Attractor at 600 kilometers per second, a tremendous velocity by any human standard. The Great Attractor lies approximately 200 to 250 million light years away, depending on which part of the structure we measure to. At 600 kilometers per second, we cover about 20 light years every million years, or about 6,000 light years every 300 million years. Simple arithmetic suggests we might reach the Great Attractor in something like 10 billion years, give or take a few billion. That is longer than the current age of the universe, longer than Earth has existed, but not impossibly long in cosmic terms. So why will we never arrive? The answer lies in the expansion of the universe itself, and particularly in the accelerating expansion driven by dark energy. While we are falling toward the Great Attractor at 600 kilometers per second, the space between us and the Great Attractor is expanding, carrying the Great Attractor away from us. On the scales we are discussing, hundreds of millions of light years, expansion becomes significant. At the distance of the Great Attractor, cosmic expansion is causing space to stretch at a rate of roughly 15 to 20 kilometers per second per million light years, based on current measurements of the Hubble's constant. For a structure 200 million light years away, this means expansion is increasing our separation by about 3,000 to 4,000 kilometers per second. We are approaching at 600 kilometers per second, but expansion is carrying it away at several thousand kilometers per second. Wait, you might think, if expansion is faster than our approach, how can we be getting closer at all? The answer is that we are measuring our motion relative to the cosmic microwave background rest frame, the natural reference frame of the universe. In that frame, we are moving toward the Great Attractor. But the Great Attractor itself is also receding from us due to expansion. The net effect is complex, depending on the balance between gravitational attraction, which pulls us together, and cosmic expansion, which carries us apart. For structures at the distance of the Great Attractor, we are currently still approaching, barely. Gravitational attraction is stronger than expansion at this distance. But the situation is changing. Dark energy, the mysterious component driving accelerated expansion, is causing the expansion rate to increase over time. As billions of years pass, expansion will grow stronger while gravitational attraction remains the same or weakens as structures become more dispersed. Eventually, within the next few billion years, expansion will overtake gravitational attraction even at the distance of the Great Attractor. At that point, despite our continued motion toward it, the Great Attractor will begin receding from us, carried away by the accelerating expansion of space. The gap between us will start to grow rather than shrink. We will never close the distance, never arrive at the destination toward which we have been falling for billions of years. This is the nature of an accelerating universe. Dark energy creates a kind of cosmic event horizon, a distance beyond which we can never reach, no matter how long we travel. Objects beyond this horizon are being carried away from us faster than we can approach them, even if we could travel at the speed of light. And as expansion accelerates, this horizon moves inward, eventually engulfing even nearby structures. The Great Attractor will cross beyond our cosmic event horizon in the distant future, perhaps 100 billion years from now, perhaps sooner, depending on the exact nature of dark energy. When that happens, light from the Great Attractor will no longer be able to reach us. It will fade from our view, not because it has been destroyed, but because the expansion of space has stretched to the point where its light, struggling to reach us, makes no forward progress, like a person running on a treadmill that moves backward faster than they can run forward. This fate awaits all distant structures. The Shapley Supercluster will cross the horizon first, being more distant, then the Great Attractor itself. Eventually, even the Virgo cluster, currently only 55 million light years away, will cross beyond reach. Billions of years in the future, all that will remain observable will be the galaxies of our local group, which are gravitationally bound to the Milky Way and will not be separated by cosmic expansion. By that time, the Milky Way and Andromeda will have merged, along with the other small galaxies of the local group, forming a single large elliptical galaxy. This merged galaxy will be surrounded by darkness, with no other galaxies visible, no cosmic microwave background detectable because it will have been redshifted to infinitely long wavelengths, no evidence remaining of the larger universe beyond. Future astronomers, if any exist, might conclude that their galaxy is the entire universe, having no way to discover otherwise. But this is so far in the future that it feels almost abstract. For now, for the next billions of years, the Great Attractor remains visible, reachable in principle if not in practice, a landmark in our cosmic neighborhood, shaping our motion even as we will never arrive at it. There is something poignant about this. Our galaxy has been falling toward the Great Attractor for billions of years, following a path determined by the distribution of matter throughout the universe, drawn by gravity toward this massive concentration. We have covered perhaps a third or half the distance already, and yet, we will never complete the journey. The destination will slip away, carried by forces beyond our control, beyond even the control of gravity itself. This speaks to a deeper truth about existence in an expanding universe. Nothing is permanent. No configuration of matter lasts forever. The structures we observe today, the cosmic web, the galaxy clusters, the Great Attractor itself, are temporary features, artifacts of a particular epoch in cosmic history. They formed from the growth of initial fluctuations, grew for billions of years through gravitational instability, and will eventually dissolve as expansion pulls everything apart. Our motion toward the Great Attractor is a journey without end, not because the distance is infinite, but because the destination is receding. We are perpetual travelers, never arriving, always in motion, following a path through space and time that leads nowhere permanent, nowhere final, only onward through the expanding universe. And yet, there is a strange peace in this realization. We do not need to arrive. The journey itself is what matters. Our galaxy's motion toward the Great Attractor is part of the grand pattern of cosmic flows, part of the structure and evolution of the universe on the largest scales. We are participants in this motion, carried along not by choice, but by the fundamental nature of gravity and expansion, playing our small part in the vast dance of galaxies that fills the cosmos. As you lie here, breathing slowly, letting these ideas wash over you, consider what it means to be on a journey without a destination. Not a journey that has failed or gotten lost, but one that never intended to arrive, where motion itself is the point, where the path is more important than any endpoint. This is not just true for our galaxy. It is true for all galaxies, all structures in the universe. Everything is in motion. Everything is temporary. Everything is evolving and changing and flowing through space according to the laws of gravity and expansion. There is no final state, no ultimate configuration, no moment when everything settles into permanent rest. There is only continuous transformation, endless motion, the eternal unfolding of cosmic history. The Great Attractor pulls us forward, but it too is being pulled by the Shapley Supercluster, by other distant structures, by the overall expansion of the universe. Nothing is fixed. Nothing is stable. Everything flows. And in that flow is a kind of beauty, a recognition that change is not a flaw or an accident, but the fundamental nature of reality itself. Our destiny is motion. Our fate is transformation. We never arrive at the Great Attractor, but we will continue moving toward it for billions of years until expansion finally carries it beyond our reach and we are left alone with the galaxies of our local neighborhood, bound together by gravity while the rest of the universe recedes into the darkness beyond the cosmic horizon. This is what awaits us. Not destruction, not catastrophe, but gradual isolation, the slow fading of distant lights, the peaceful transformation of a complex, connected universe into a simpler, lonelier one. And all of this will unfold over time scales so vast that they make human history, even the entire history of life on Earth, seem like the blink of an eye. For now, we move forward through the night, pulled by invisible forces toward a destination we will never reach, riding the cosmic currents through an expanding universe, participants in the greatest journey of all, the evolution and transformation of the cosmos itself. As we come to the end of our journey through the story of the Great Attractor, let your mind settle into stillness, your breathing slow and even, your body completely relaxed. We have traveled across hundreds of millions of light years, explored structures containing the mass of thousands of galaxies, traced the flows of matter through the cosmic web, and contemplated our galaxy's destiny as it falls through space toward a destination it will never reach. Now, in these final moments, let us reflect on what this means, not just for our galaxy, but for our understanding of the universe and our place within it. The Great Attractor is invisible, hidden behind the dust and stars of our own galaxy, revealed only through patient observation and careful reasoning. We cannot see it directly, not in its entirety, yet we know it is there because we can measure its effects. We feel its gravitational pull in the motion of our galaxy and thousands of others. We infer its presence from the flow of galaxies converging toward it from all directions. This is a powerful metaphor for much of what shapes our lives and our universe. So many of the most important forces, the most fundamental influences, are invisible. Gravity itself cannot be seen, only its effects. We cannot see the curvature of space-time, but we can observe how matter and light respond to it. We cannot see dark matter or dark energy, the components that make up 95% of the universe's total energy content, but we can measure their influence on galaxies, clusters, and cosmic expansion. In our own lives, we are shaped by forces we cannot directly perceive. The pull of family and culture, the currents of history, the invisible frameworks of meaning and value that guide our choices. All of these shape who we are and where we are going, yet they operate in the background, unseen, like the Great Attractor pulling our galaxy through space. We are all travelers on journeys we did not choose, carried along by motions we cannot control, influenced by forces far larger than ourselves. And yet, there is freedom within this motion. A galaxy falling toward the Great Attractor is not passive. It rotates, forms new stars, sends out light into the darkness. It lives in its own vast and timeless way, even as it is carried along by cosmic currents beyond its control. You too are in motion, always, at every scale. Your body moves through space as Earth turns and orbits. Earth moves as the solar system circles the galaxy. The galaxy moves toward the Great Attractor. And beneath all of this, your cells move, your blood flows, your thoughts drift from one idea to another, never still, always in flux, always changing. There is a deep restfulness in accepting this motion, in recognizing that stillness is an illusion, that everything flows, that the universe is not a collection of static objects, but a network of processes, a web of transformations unfolding across time. The Great Attractor is not really a place. It is a process, a concentration of mass that emerged from initial fluctuations, grew over billions of years, shaped the motions of surrounding galaxies, and will eventually dissolve as cosmic expansion pulls everything apart. It is temporary, like everything else, a pattern in the flow of matter through space and time. This temporariness is not sad. It is simply the nature of things. Nothing lasts forever, but that does not diminish the beauty or importance of what exists now. The Great Attractor is real. Its influence is real. The motion it creates is real. That this configuration is temporary, that billions of years from now it will have changed beyond recognition, does not make it any less significant in this present moment. We are all travelers on journeys we did not choose, carried along by motions we cannot control, influenced by forces far larger than ourselves. And yet, there is freedom within this motion. A galaxy falling toward the Great Attractor is not passive. It rotates, forms new stars, sends out light into the darkness. It lives in its own vast and timeless way, even as it is carried along by cosmic currents beyond its control. You too are in motion, always, at every scale. Your body moves through space as Earth turns and orbits. Earth moves as the solar system circles the galaxy. The galaxy moves toward the Great Attractor. And beneath all of this, your cells move, your blood flows, your thoughts drift from one idea to another, never still, always in flux, always changing. There is a deep restfulness in accepting this motion, in recognizing that stillness is an illusion, that everything flows, that the universe is not a collection of static objects, but a network of processes, a web of transformations unfolding across time. The Great Attractor is not really a place. It is a process, a concentration of mass that emerged from initial fluctuations, grew over billions of years, shaped the motions of surrounding galaxies, and will eventually dissolve as cosmic expansion pulls everything apart. It is temporary, like everything else, a pattern in the flow of matter through space and time. This temporariness is not sad. It is simply the nature of things. Nothing lasts forever, but that does not diminish the beauty or importance of what exists now. The Great Attractor is real. Its influence is real. The motion it creates is real. That this configuration is temporary, that billions of years from now it will have changed beyond recognition, does not make it any less significant in this present moment. The Great Attractor is pulling our galaxy through the darkness. We move toward it at 600 kilometers per second, a motion that began billions of years ago and will continue for billions more, though we will never arrive. This motion is beyond our control, beyond our awareness in daily life. Yet it is real and constant, shaping our journey through the cosmos. In the same way, there are forces in your life, influences you may not fully see or understand, that shape your path, that pull you forward through time, that guide you toward destinations you may never fully reach. This is not failure. This is the nature of existence. We are all travelers, all falling through space and time, all pulled by invisible forces toward uncertain destinations. And there is peace in this. You do not need to control everything. You do not need to see every force that shapes your life. You can simply be, like a galaxy drifting through the cosmic web, following your path, living your moment, part of the great pattern that connects everything. Let your breathing deepen. Let your body sink into complete relaxation. Imagine yourself floating in the vast darkness of space, surrounded by stars, drifting slowly, gently, carried by currents you cannot see but can feel, moving through the night toward a distant point of light that grows neither closer nor farther, always present, always ahead, a beacon guiding your journey through the infinite. The Great Attractor calls to us across hundreds of millions of light years. We answer with our motion, falling through space, not alone but accompanied by millions of other galaxies. All of us participants in the grand dance of cosmic structure. All of us pulled by gravity through the expanding universe. All of us temporary patterns in the eternal flow of matter and energy that is the cosmos itself. You are part of this flow. Your atoms were forged in ancient stars, scattered through space, gathered into planets, assembled into living forms. You are stardust, organized temporarily into consciousness, aware of the universe that created you, capable of understanding your place in the vast web of existence. And now, as sleep approaches, as your thoughts slow and soften, as awareness fades into rest, you can release your hold on all of this. Let the Great Attractor pull you gently forward. Let the cosmic web support you. Let the motion carry you through the night. You are safe, held by forces older and stronger than you can imagine, drifting through space and time on a journey that has no end. Only continuation, only flow, only the eternal now of existence unfolding moment by moment by moment. The invisible hand that pulls our galaxy through space pulls you too, not physically, but metaphorically, toward rest, toward peace, toward the quiet dissolution of thought into sleep. Let it pull you now. Let go. Drift forward through the darkness. The Great Attractor awaits, patient and eternal, and you are already on your way, already moving, already exactly where you need to be. Sleep now. The journey continues, with or without your awareness. The universe flows on, and you flow with it, part of everything, connected to everything, pulled gently forward through the infinite night, toward morning, toward awakening, toward tomorrow. But for now, only this moment, only this breath, only this gentle falling into rest.